Well, I'm kind of on a roll today, so I figure I'll keep making videos until I'm too tired. Looks like I already am because I can't spell combinatorics. I'm not going to go really deep into it, but I do want to give some preface because it's important that you at least kind of understand what combinatorics is. I'm going to go over factorial and choosing. You don't need to know what those are right now. We'll get into it. So, what is combinatorics? I already wrote that. Combinatorics. It is a fancy word for counting. And counting's pretty easy. 1, 2, 3, 4. Well, that's not so bad. But what if I asked you this? There is an open position. No, there's not just one. There are 3 open positions at Google, all for web developers. Not three. Let me actually undo that. 5 different people apply for all 3 positions. So in essence, it doesn't matter which order you hire them. So let me make this clear over here. So let's say we have 5 people over here. I'll label them 1, 2, 3, 4, 5. And there's web developer number 1. There's web developer number 2. And there's web developer number 3. So basically what I'm saying when I say that all positions are the same is that it doesn't matter if you have this guy go to position 1, this guy go to position 2, and this guy go to position 3. Or if like somehow you were just to switch these guys, that doesn't make a difference. Those are counted the same. So basically the way you could think about it is that there's 3 boxes for position number 1, position number 2, position number 3. And these are the people. And if you put, I don't know, the second person here, or the 4th person here, and the 5th person here, that is exactly the same as hiring 5 to 4. Because they have the same people hired and the positions are the same. So we wouldn't count that twice. If we counted this as a case and then we counted this as a separate case, we would have overcounted. So my question is, how many possible ways can Google hire out of this pool? And we're going to assume that they fill every position. We're going to get into that. This is the problem that we're going to try to solve before the end of the video. First, I need to talk about factorial. Hopefully that example shows you why counting can be more tricky than just going 1, 2, 3, 4, 5. Because you don't even know when to stop. So let's just talk about factorial and we'll get back into this problem. N factorial. This is defined as n times n minus 1 times n minus 2 times ... times 3 times 2 times 1. Sometimes you'd rather think of it this way, or sometimes you'll think of it, that's descending, but it's exactly the same if you were to go 1 times 2 times 3 ... times n minus 1 times n. For example, 6 factorial is equal to 1 times 2 times 3 times 4 times 5 times 6. Good. Oh, so now you might be thinking, okay, that's great, but what's the significance of this? Why do I care about what factorial means? Well, it's an ugly color, and I want to choose that color. Factorial means the number of ways you could arrange n distinct objects. What do I mean by that? Let me scroll over. I've run out of space going downwards. Now I have to go sideways. What do I mean by the number of ways you can arrange n distinct elements? So let's say I had person A, person B, and person C. And I need to seat them. There's a seat here, there's a seat here, and there's a seat here. Maybe I seat person A here, person B here, and person C here. Just in that order. Well, I could also do it this way. I could also do A, then C, then B. Okay, well, that's all the ways I could put A in the first spot. What if I started with B instead? I could do B, then A, then C. Okay, that would work. Or I could do B, then C, then A. Right? Okay, well, what about C? I could put C first because I've exhausted all the possibilities where A is in the first position. Now I've exhausted all the possibilities where B is in the first position. Notice I also can't repeat a letter because there's only 3 people available. I go C, A, B, and then I have C, B, A. So I had 3 elements. And how many ways could I arrange them? Well, 1, 2, 3, 4, 5, 6. And it is no coincidence that 3 factorial is equal to 3 times 2 times 1, which is 6. Okay. Let me clear this. I will eventually get back to the Google problem. Why, though? Why does factorial behave this way? Well, think of it this way. Say I have person 1, person 2, person 3, person 4, person n, and I need to arrange them so I can put them into n slots. I can put them in the first slot, or the second slot, or the third slot, or the fourth slot, ... into the nth slot. So let's say that I just decide to choose them in a particular order. Well, if I make the first choice, I have n options. I could put n people here. But once I make that decision, I have 1 less choice. Let's just say I chose this guy. Well, now I have n minus 1 choices when I choose where the second person goes. Once I make that choice, I've removed someone from the pool. Now I have n minus 2 choices. Now I have n minus 3 choices. I just keep doing that until the very end, and I only have 1 choice. And clearly, this is and when you want to figure out how many possible ways you could do this, it's n times n minus 1 times n minus 2, all the way down to, down to 3, 2, 1. And that is n factorial. Let me stop circling stuff. As n factorial. So that's why n factorial behaves this way. Okay. I think I've run out of time, so I think I'm going to leave the Google example. I'll leave the Google example next time. But hopefully you understand how factorial works. Next time we're going to be talking about, we're going to use factorial to construct a new function called the choose function. All right, I'll see you there.